all the documents to you at the end of the day. Yes. Because it's either you or me who has to put this and disappear. What it takes here, right? So just have to see the text and
I
might type it on the computer. We will attach the documents. Correct? I might type it on the computer. We can print it and attach. You can print. I don't know how to do it, but the IT support first and the last.
So you cannot see that there's Laure and Julie connected, but they're still missing Andy. Maybe I can ask first. Sorry, Laure and Julie, can you hear me fine?
Yes, it works. I can hear you fine.
Yes.
I also hear you correctly.
Sorry, I cannot.
Do you hear me?
Can you talk now? So I see if I can hear you.
Yeah. Do you hear me?
Merci.
Is it okay?
Yeah, perfect.
Okay, thanks.
We're just waiting for the last jury member to connect.
Hello. I'm Ben Wandelt. I've just been designated the president of the jury. You were not there when that happened. Is it okay if I take the role of president of jury?
Yes, of course, it's okay. Thank you.
It's perfectly okay.
Okay, and the third?
Yeah, Andy is still not connected.
He's not connected. Okay, I'll ask him later. Thanks.
Okay.
Oh, he just connected.
Hi there.
Hi, Andy.
Oh, okay.
Hi, Tobias.
Hi. She's going.
Hi, Andy. This is Ben Wandelt.
Hi, Ben. How you doing?
Good. How are you?
Good to see you.
Likewise. So I've just been designated the chair of the defense committee. Is that okay with you?
That's perfectly fine by me.
All right. Good. Thanks. I think we can almost get started.
Yeah. Okay. Okay, can I ask you to mute, please? Right, thank you.
Is it the time? Okay. Bonjour tout le monde. Est-ce que j'ai un microphone, un micro pour... Est-ce que vous m'entendez bien en ligne?
Oui.
Oui, ça va?
Ça va.
Ok.
Ça va. Il faut parler fort.
Bon, je vais peut-être mon mieux. Alors, bonjour tout le monde. Hello, everyone. We are here for the soutenance de thèse of Tobias Liaudat. And we will start with his presentation of his PhD subject.
Okay, thank you very much. Okay, we'll start. So welcome everyone. I'm going to present you the work I've been doing during the last 3 years. And the title is the data-driven Poisson function modeling of ground-based and space-based telescopes. So let me start with some context and motivation. So first, here you can see the lambda CDM cosmological model that is our current standard cosmological model that has been very successful in explaining many of the observations we have seen. However, there are still some open questions in this model. For example, if we try to infer the cosmological parameters with early time or late time observations of the universe, we found significant tensions. There's also the origin of the accelerated expansion of the universe, as well as the nature of dark matter, for example. In here, you can see the energy matter concentration of the universe. You can see that it's mostly dominated by dark matter and dark energy, with only 5% of visible matter, which is what we actually see every day. And it's very hard to study dark matter and dark energy by their due to their properties. For example, dark matter has no electromagnetic interaction, so you cannot actually see it. However, this matter has some gravity, and you can use that to probe it. And how are we going to do that? Well, we're going to profit from this gravitational lensing effect. Here you can see some foreground galaxies emitting photons towards us, and there's a big concentration here of dark matter or some massive object, and it's going to deviate the path of the photons, and the effect in from our observer looks like this, as you can see. That is distorting our images of the foreground galaxies. And in fact, we're going to use these galaxy photons to probe dark matter. And to do this, we are really interested in measuring the shapes of galaxies in order to estimate these deformations. So we're going to use these galaxy shapes as estimators for this gravitational shear, that is this deformation due to this gravitational lensing effect. So we start with an intrinsic galaxy, and we need some type of descriptor to be able to quantify this deformation. So in this case, we're going to use the ellipticity. So this has two components. Here we can see how does the two components of ellipticity change a circle as we modify them. And then we have this galaxy that has some intrinsic ellipticity. Okay, so we're going to observe this galaxy is going to go through the process of shearing that's going to deform this shape. Then the PSF is going to affect this observation. So it's going to blur this image. Then we're going to have the pixelation effect when you're observing some type of detector, and finally add some noise, and we arrive to our observations. So we're going to try to measure the shapes on our observation. That is what we dispose of. However, a naive shape galaxy measurement will measure some hat ellipticity that will be composed of the intrinsic ellipticity of the galaxy plus a term that will depend on the shear. However, and we are interested in estimating the shear here. However, we don't know any of both of them beforehand, so it's very hard to estimate both of them from one single galaxy observation. What we can do is use many galaxy observations and build an estimator of this shear quantity. Why? Because this shear is applied systematically to every galaxy, and we can assume that the intrinsic galaxy has a random distribution with a zero mean. So our shear estimator looks like this. However, here we are forgetting about the effects of the PSF here. Therefore, we have another term that is added to this galaxy shape measurement that is affecting the shape of the galaxy, that is due to the PSF. And as it's also systematically added to the observations, we can find it here on our shear estimator. And luckily, in the weak lensing regime, the PSF deformation can be even bigger than the shear. It's actually important to take this PSF into account in the shape measurement. Why? Because if we take it into account, we can directly measure the shape, that is only the intrinsic ellipticity and the shear, and then retrieve again our unbiased shear estimator. However, we need a PSF model for this. And now we're going to introduce a little bit what is the PSF, which is the point spread function. So actually it's the impulse response of the system. So we have an impulse, we put it as an input of the optical system or imaging system, we find the PSF that can look like that. We set actually a measure of the quality of the system. So for example, the broader the PSF, the more the resolution will be limited on the system. Let's also include the diffraction phenomena. And if we're considering incoherent light, which is the case with most of the natural sources that we're going to study, the system is linear in intensity, which is actually very practical, and the PSF acts as a convolutional kernel. So you have two objects A and B imaged by some type of system, and then the output we're going to see the PSF convolved with A in addition to the PSF convolved with B. So, but this convolutional kernel is not the same for every position in the field of view. It's actually a field, and it's going to change as a function of the position and as a function of wavelength and time. So there are several contributors to this PSF field. For example, the lenses or the mirror sizes, optical aberrations, obscurations, and detector level effects. And all of this will contribute to the profile of the PSF. Here you can see different type of PSF, where here you can see a PSF that is diffraction limited, which means that what is limiting the resolution on the system is the diffraction effect, which is not the case on the other ones. And also there are some spatial aberrations of the PSF, so this kernel is changing in the position of the field of view. There's also diffraction phenomena, reflection, and refractive components in the system, so will contribute to the spectral aberrations of the PSF. So how does the PSF change as a function of wavelength? And also the atmosphere and some mechanical variations that include some temporal variations of the PSF on top of all the others. So now we're going to go through the observational model that we're going to consider. So in our field of view, in a wide field of view, we have some galaxies that are our objects of interest, where we have our PSF field at some position on wavelength is going to be convolved with this underlying object. Then we're going to integrate these in wavelength. And then after some degradations and adding some noise, we recover our observations. So remember that we wanted to estimate the PSF field to have a PSF model. However, it's very hard to estimate this PSF field directly from the galaxy observations. Why? Very simply because we don't know actually the shape of the galaxy, and we don't know the PSF field. Therefore, trying to estimate these both quantities is very hard. Luckily enough, there's also stars in the field of view, and these stars can be assumed to be point sources. That is very practical in this sense, that want to help us to constrain our model, because these represent some degraded samples of the PSF field. So if we change the equation here, now we can see that we have directly the PSF with a point source, with a spectral energy distribution here, that is just kind of the point source has different energies at different wavelengths. So we can replace this, and we have this equation that gives us the model to observe each star. And at the end, okay, PSF modeling consists in building an estimator, a PSF model estimator from these samples, and then using this estimator to compute the PSF at the target positions. And that is what we're going to talk about today. So here you can see an example of a recent taken gravitational lensing picture. You can see here an example of a lens galaxy with a massive object on the middle, and an example of the PSF from a bright star. However, this is actually strong lensing. A weak lensing image observation looks more like this, which is actually taken by the Thesis survey. And if we zoom in, you can see a more zoomed in picture and ask, where are the lensing galaxies? Well, and the question is, in fact, the shear is very small, so we cannot actually see them directly by eye. Therefore, the PSF, when you want to try to correct and estimate a model of the PSF, needs to be very accurate in order to correct and have an unbiased estimate of the shear. This is going to be the introduction to modeling the PSF for ground-based telescopes. So we recapitulate a little bit what variations we need to model in the PSS. We need to model some temporal variations, some spectral variations, and some spatial variations. For the temporal variations, it's actually simple what we can do. We can just take a snapshot in time, one exposure, and use all the stars that are there to estimate the model. This just limits the number of available stars, but it's okay. For the spectral part, in the ground-based service, mostly we are working with narrow band filters. And also we have the effect of the atmosphere, that low band pass is it's kind of a low pass filter of the PSF. So at the end, you can kind of ignore the spectral variations for the level of accuracy that we are looking for space-based, for ground-based service. However, we still have to model the spatial variations of the PSF. Here you can see an example of a wide field of view imager used in Thesis, that is 1 square degree. And there are significant spatial variations in this instrument because it has a very wide field of view. So we can tackle this problem using a matrix factorization approach. So here is an example of a more general system that you can think of. So you have some features and some weights, and then our observations will be built in this way. We have some features that are going to be shared by all the stars, kind of some type of principal components, but not necessarily, and then some weights that will define the spatial variations of the PSF. So then to reconstruct the observations, what we need to do is just use these features after we learn them, and then these weights, the observation will be a weighted sum of these features with the weights corresponding to the spatial variation. Then we have some degradation operator and define our observations. These models differ in different things. Which regularization do you take? Which optimization procedure do you use to estimate the parameters of the model? Which spatial variations are you considering? And they are usually built on the pixel space, and normally they are done on a single CCD, and they're independently on a single CCD. So, okay, which types of variations do we need to model? We need to model some type of global variations, which are, for example, the instrument optical system. Here you can see the contribution of the optical system to the first component of the ellipticity in the focal plane. You know, see these spatial variations, and there are some spatial correlations between them. Also the atmospheric variations that due to the atmosphere, the changes in the atmosphere during the observation, and also some local variations due to the CCD. Typical models are using, they're only using a single CCD to model this field. There are independent models for each CCD. So actually these, the global variations are not really well modeled by this, as we are neglecting all the spatial correlations that are on this focal plane. And also it actually limits a lot the number of stars that you use to constrain the model, because we are just using the stars of one single CCD. And actually that just limits the models that you can use, because you don't have enough information to constrain a complex model. So here I have developed a new model that's called multi-CCD PSF model with some contribution that you can see over here, where we're going to handle both types of variation. What we're going to do is use a common coordinate system. We're going to learn global and local features for different types of variations. So here you can see the equation of the model for a 1 CCDK. We have a local part of the model and a global part of the model. Here S represents the features of the model. So here you have an example of one of the trained global features and one of the local features. And then for the spatial variations, what we're going to do is to do a subsequent matrix factorization here that we're going to define a spatial variation dictionary. That's going to be here DK, for example, or PK, depending if it's local or global. And this spatial variation dictionary, how are we going to build it? We're going to use some polynomial spatial variations that normally are good for modeling spatial smooth variations, and also some gray spatial frequencies that can capture more localized variations. And then we're going to use this sparse weight matrix that help us to enforce a feature to be learned and specialize on a specific variation, and model the PSF capturing the information on that specific variation. So some words about this graph-based constraint that we had before. So we are considering an undirected, fully connected graph, weighted graph. So with the graph nodes are the star positions, and the graph weights are just, we define them using a parametric function of the star distances, that's more of the inverse of the star distancing. Then we just compute the graph Laplacian, and we can compute it. It's a symmetric semi-definite positive matrix, because the graph is fully connected, and the eigenvectors are the base of this matrix, are the base of the graph Fourier transform. And you can use this to construct one of the spatial added to the spatial variation dictionary. And then you can do this for several graphs to consider different type of variations and build this one part of the spatial variation dictionary. Then we have to consider which type of regularization are we going to do to the system, because we have a problem that is ill-posed, an inverse problem that is ill-posed. We have noise on observations. We have not enough stars to constrain the model. So which constraints are we going to consider? We're going to consider the positivity over the PSF, as we know that the PSF is a positive kernel. We're going to consider the structure and the smoothness of this profile, for example, enforcing the features to be sparse on a given wavelet basis. So actually that's very related to the noising. And also we're going to consider the regularity of the PSF field, as I mentioned before, with the spatial variation dictionary. And we're going to use also some dimensionality reduction technique by setting up a low number of features. So I want to constrain the model. So here you can see an example of what all this equation looks like. We have several terms from different parts of the model, but now the question is how we're going to optimize this. We have a non-convex and a non-smooth problem, and we want to estimate all the features here, the features and the weights defining the spatial variations. How we're going to optimize this? Well, it's non-convex, but we can profit that this is actually a multi-convex optimization problem, because the non-convexity is coming from this multiplication of the matrices. It's a matrix factorization. We have two matrices multiplying, and if we fix one matrix and optimize over the other, we have a convex problem. So we can actually profit from this to solve the problem, which is actually one type of block coordinate descent method. And then each of these sub-problems is actually a convex non-smooth problem. And we can tackle this using some type of proximal algorithms like Pfister or contact view that are widely used. And at the end, the optimization algorithm looks like this. We have a general iteration where we first go optimizing over the global features on this block coordinate descent method. And then we repeat that, but for the local features to correct for the difference. And we go over every CCD, so every CCD iteration, and on the block coordinate descent iterations. And then we iterate over that until we converge. So before continuing, I'm going to introduce you the Canada-France Imaging Service, Thesis, where we have applied this model, and it's one of the motivators of this model. So it's located at the Canada-France Hawaii Observatory using a 3.6 meter telescope that you can see here. It uses MegaCam, which is a wide field imager of a 1 square degree. And the PI of the project is Jean-Luc Starck from the CA. And it's got the main purpose is to provide photometric support for the Euclid mission on the air and U bands. However, this survey is wide, as you can see here, how the area that is going to cover in the northern hemisphere is also deep, and it also has a great image quality, where the image quality is measured on the width of the PSF. That because the PSF in that case also considers the atmosphere at that location. So it is actually a great candidate to do weak lensing. So actually there's quite a challenge in working with real data. So in our lab in Cosmologists, we have developed a shape pipe, which is an automated shape measurement pipeline for weak lensing, where the code is available. And I have contributed to this pipeline with the PSF modeling and all the validation part of the pipeline, and including the MCCD PSF model. That was quite some work because you have to handle outliers working with real data. Also, you need to measure like the connections with other methods have to run smoothly, and all the assumptions that are taken in the other methods have to be respected. And actually, we have validated the model performance. We have obtained a gain in 22% over the previous state-of-the-art method that was already implemented in the pipeline. And we haven't not only validated the PSF model in itself, but validated the PSF model within the shape measurement pipeline and within the shape measurement task that was actually the purpose of the method, to contribute on having a good shape measurement using this new model. You can see some contributions over there. And actually, we have used the model, which is very nice, to produce a new weak lensing catalog using the MCCD PSF model that spans almost 3,500 square degrees, which is actually one of the biggest catalogs up to date. Has run, for example, more than 3 months in one of the very big Canada's computing center. You can see here the area covered, and there's a contribution in place. Here I'm going to show you some of the plots produced by the PSF validation part of the pipeline. On the left here, you can see here's for the first component of the ellipticity. You can see the contribution of ellipticity of the stars measured on the stars for each point on the focal plane when we average over many exposures. So we kind of lose all the the spatial variations with a non-mean with a non-zero mean. And here you can see the residual with respect to the model. But you can see that we are 1 order of magnitude lower than the actual stars. You can these residuals you can see here that the model was not able to model. You can not even see them here. So actually, in fact, it's a very good modeling. And here you can see the same plots, but for the second component of the ellipticity, which is even lower. So here I'm going to go with some preliminary conclusions on this part. So we have developed a new PSF model, which includes the instrument geometry on the PSF model, and it's based on a constrained matrix factorization scheme, where the code is available. We have validated the model with simulations and then applied it to real data, and used it to build one of the largest weak lensing shape catalogs. So now the question is, okay, can it be a solution for the Euclid mission that is about to launch soon? Well, in fact, not really. Why? Because it's very hard to model super resolved diffraction limited PSF. So here you can compare an observation in the Thesis survey, an observation in Euclid, a super resolved Euclid star, and we are still not able to model the PSF chromatic variations. Here you can see, invite you to see this example, where here you can see an image, and here you can see another image that is the same part of the sky, and you can ask yourself, what is the main difference? And in fact, the main difference here is the atmosphere. So we are both observations of the same part of the sky, but one with the James WST telescope, and the other one with the Thesis survey that we were using. So now, actually, losing the influence of the atmosphere is one of the main motivations to go to space. And that's why right now we are going to space and model the PSF to our space mission. And we're going to focus on the Euclid space mission. Why? Because actually a mission is optimized for weak lensing. It's one of the main scientific goals. And actually the PSF model is a crucial part of the mission. Why? Because it's on the base of the building of the shape catalog. And if we have some errors on the PSF model, we have some bias on these shape catalogs, and will propagate through all the cosmological analysis. This mission is going to observe a vast part of the sky, so we have to control the computing time of the models. We are also having some more complex diffraction limited PSF. We are close to the diffraction limit, and the observations are undersampled. So this is another difficulty that we have to tackle. Here is an example of one observation, and here is example of the super result of this observation. That is a 3 times super resolution that we need to do to be in adequate sample in all the band of Euclid. And actually the band, the Euclid base broadband, is from 500 to 900 nanometers, which is very broad. And this obliges us to model the chromatic variations of the PSF. So actually this is what we're going to model, a super result PSF as a function of wavelength. And actually this mission has very, very low error requirements. And just to make an example, before I started my thesis, the state-of-the-art method in data-driven PSF modeling was 300 times over the requirements in terms of shape and 10 to the 4 in terms of size, just to make an order of magnitude of where are we. And actually there are many new challenges arising with this survey. So actually, let's go again how we're going to model the PSF field for space-based telescopes. We have to model 3 types of variation again. However, one approach is to build a parametric model, which is actually where you build a physical model of the system, of the optical system, as close as you can from the reality, and then consider many physical phenomena as you can, and model this actually can model the PSF chromatic variations. However, it's hard to constrain from observations. Also, this computationally very expensive because there are many terms involved, and it's actually sensitive to mismatches between the model and the observations if some of the underlying hypotheses of this model are not respected. Also can require expensive calibration data. This is actually only possible for space-based telescope because you cannot model in this way the atmosphere, is very hard. And it was developed for some space-based telescope like the Hubble Space Telescope, and it's currently being developed for Euclid. So here I'm going to try a different alternative approach, that is the data-driven models. I'm going to try to see and try to show you that this can actually be complementary to the parametric models. And how can they work together? So actually the spectral variations in a data-driven approach is very hard, especially when the passband is so broad as in Euclid. Here you can see, to have an example, the spectral variations of the PSF. Here, if we integrate it in wavelength, and here, if we undersample. And we have from observations like this, with some noise added, we have to model all this complexity. So doing that in a data-driven way is very hard. So there was some previous effort trying to model this using optimal transport. For example, trying to define this as an displacement interpolation from the 2 extreme PSF, but it was not very effective. So the proposed approach I'm going to follow is trying to include the physics of the problem, but then trying to remain data-driven. How are we going to do this? Well, we're going to build an optical forward model, and then we're going to remain data-driven. We'll need to make it differentiable. So here are some words of how we're going to obtain the gradient through automatic differentiation. Going to automatic differentiation, you can define an expression with some parameters, and we want to compute the gradients of this expression with respect to these parameters. Normally, this function is built as a sequence of fundamental operations, and you actually end up building some type of computational graph. And then, as we know these analytical gradients of the fundamental operations, we can use the chain rule to automatically compute the gradients that we are interested in. We just need to code this expression in an automatic differentiation framework like TensorFlow, and voila. Then you can remember that automatic differentiation is not numerical differentiation, it's not either symbolic differentiation, and that the gradients are exact. So I'm going to now come again back to how we're going to model the PSF field in this new way. We're going to change the representation space of the PSF. So before we're modeling the PSF on the pixel, so in intensity representation, here we're going to go through something that's called the wavefront error space. Here you can see an example of the Euclid optical system, which is actually very complex. It has many mirrors and many effects going on there. However, we can consider an alternative simplified model of a single lens that has, as in the first order, the same effect of this optical system. And in considering this new simplified model, we can define what is the wavefront error space. Here you can see in a projection of the image, you can see you have some plane incoming plane wavefront coming to our new single converging lens. So that you can see here, this converging lens, its task is to make these plane wavefronts into a spherical wavefront that will actually end to converge in the focal plane. Ideally, will converge in a single point, but there are some aberrations in this optical system that will make them have some differences between the ideal spherical wavefront and this aberrated wavefront. And this difference that you can see here between the ideal and the aberrated wavefront is what we call the wavefront error space. And we can represent the PSF that we are observing as this wavefront error map. Actually, this, then once we have this, we can propagate it to the focal plane, take the intensity, and we regain again access to the pixel PSF. That was what we were interested in. We're going to use this space to model the PSF. I have proposed a new model I've built from scratch that is called the wave diff PSF model with some contributions, and the code, of course, is available, where we're going to describe the PSF as two parts. We're going to have a parametric part and a non-parametric part. The idea is to build the model in the wavefront, directly in the wavefront, and as it is going to be much easier to model the chromatic variations while still being data-driven. However, it's harder to constrain from star observations. The idea is that the parametric part of the model can be estimated or also can be an input of the model. And then the non-parametric part will have as a task to correct the mismatch between this input part or the parametric part and the observations. We're going to build an optical forward model based on telescope optics, which the task is to propagate these wavefront error maps until the pixel error, until the pixel PSF that we are used to see. That will include the diffraction phenomena, which in Fraunhofer approximation, the obscuration, downsampling, many effects that's going on the optical system. It's going to be end-to-end differentiable. It's going to be entirely coded in TensorFlow, and also allows fast computation on the GPU, which is very, very nice. Here is an overview of the approach with some building blocks. So we can start on the left. We start with some position on the field of view, and the PSF model is going to give us the wavefront error representation of the PSF at this position. Once we have this wavefront error representation, we can propagate it through the optical system and obtain our pixel PSF. Here in this case, we have a pixel PSF at a high resolution space. So we have the pixel PSF at the resolution that we really want and at a single wavelength. Then we're going to suffer several degradations, for example, integrated over the broadband, also downsampling to the observation resolution. And in that moment, we can have a reconstruction that we can compare to the observations of the stars observed on the field of view. Once we have both of these, okay, we have gradient, we can propagate the gradient throughout the model because it's automatically differentiable, and we can have a loss and then estimate the parameters of the model, differentiating through this loss. And then at the end, we can just input a new position in the field of view and estimate the PSF at the target position. I'm going to focus a little bit on this part of the model, the PSF model and the optical propagation. So here you can see the equation that defines this model and the propagation. So you can see here on the right, the parametric and the non-parametric part of the model. Both of them are going to be based on a matrix factorization approach, where now the features are not going to be PSF features, but wavefront error features. And we're also going to use some type of spatial variation dictionary. For the parametric part, we're going to use fixed features, so we're not going to train them, and they're going to be used as Zernicke polynomials that are orthogonal in the unit disk and very used in optics. They look like this. And for the field of view variations, we're going to use field of view position polynomials. Then for the non-parametric part, the features are going to be completely learned from the data, and they look like this, for example, where we're going to use for the spatial variation dictionary, going to be different spatial variations will define different flavors of the model, for example, like some position polynomials, some graph-based variations, or using both of them. Here you have some examples of how do these contributions looks like. Then you add the telescope's obscurations that affect the shape of the PSF. And also you have this diffraction operator that will be the part that will propagate the PSF through until the focal plane, which actually, in fact, if we want to do this following the typical equations, we will need to resample the wave frontier space for each wavelength. However, here we have implemented a way where we avoid this resampling, which is much faster, which is just adding a wavelength-dependent zero padding. In fact, if we add a different zero padding as a function of wavelength, it has an effect of a resampling on the wave frontier space, which is actually nice because it's fast, differentiable, and it allows you to control the sampling. So you can make sure that we are Nyquist sampled all the time. And at the end, okay, we have our PSF at a single wavelength and at a good resolution. Here we are also considering the PSF chromatic variations due to diffraction that are this term over here. That could be replaced for some other time if we want to include more effects. How are we going to optimize this model? Actually have a model that is non-convex, is high dimensional, it is non-smooth, so it's actually harder. And here we don't only have the matrix factorization non-convexity, but also the forward model is actually non-convex. Well, we have a highly overparameterized model in space. So in fact, observations are 32 by 32, but our wave frontier space features are 266 times 266, 56. So we're going to use some type of optimization procedures that are very popular in machine learning, which are actually some type of stochastic gradient descent. So here you can see which type of loss function we are going to use. It's just a weighted mean squared error loss with the noise standard deviation estimated from the observations, and some regularization depending on the model flavor. Depending if you have the graph part, you have to add a L1 loss. And we're going to tackle this using a rectified Aram algorithm. That's actually a type of stochastic gradient descent method that is usually used for training neural networks. Then for the PSF recovery, how we're going to recover the PSFs, you're going to be straightforward and fast. Just evaluate this PSF model at a new position and you can propagate it through the forward model. So let's go through some of the experimental setup that we're going to consider first. We have in this scenario. So the PSF field is more complex than the PSF models. This means, which is interpretation, where there are some unexpected complexity occur, and we have to see how the model reacts because we have not anticipated something that happened on the telescope, which can actually be the case. We're going to simulate one simplified Euclid field of view with a bunch of stars. We have to do an undersampling of 3 times. Here's a example of a ground truth wave frontier, a ground truth PSF at 3 times the observation resolution. This is our target. Example of some observations with different a flat distribution of noise, and some real SED templates that we're going to use to generate the data. So which models are we going to compare? We're going to compare some wavefront-based models, so using this forward model. So the first 2 models represent just the parametric part of the model. One is going to have a very misspecified parametric model, so only using Cernic polynomials up to the order of 15, where the ground truth is made up to the order of 45. And then a Cernic 40 that is just a slightly imperfect parametric model. Then we're going to use these proposed wave diff models that will have using the misspecified parametric model and the data-driven features that will hope that they can reconstruct, help in the reconstruction of the PSF field. And then some pixel-based models on some standardly used models and previously the one I presented before. So I'm going to show you here some of the performance results. You can see here the reconstruction at Euclid resolution and at super resolution. On percentage, you can see the relative error that is more illustrative. And you can see that there is also already a performance gap between the wavefront-based models and the pixel-based models. You can see here, especially on the super resolution step, you can see here around 40 or 50 or 60, and here up to 1.3%. It's actually impressive. We have reduced the pixel error at both resolutions several times, even like 44 times at super resolution. And we can see here an example that the wave diff original is the best one performing, that is just using the spatial variation polynomials. And it's interesting to see in this model that it's actually using this part of the parametric model. So actually the difference in performance between here and here, or here and here, is what the data-driven part of the model is contributing. So this is illustrating the importance of having this data-driven part in the model. Actually constitutes one breakthrough in performance of the data-driven PSF modeling for space telescope. So now one question you might ask is, okay, this is in terms of pixel-based metrics, but how are we doing in reconstructing the ground truth wavefront error? Well, actually, no. Just before, that's our assumption on this problem. The scenario was that none of them can have a 0 reconstruction error. Why? Because the PSF model complexity was lower than the ground truth. Okay, but what do we do? Well, actually very bad. The models have very high wavefront error, over 100%, all of them. So in this current scenario, we can ask our question, actually, should the model aim to estimate this ground truth wavefront error? Well, some answer is that, well, not necessarily. What we are interested in having and giving to the next part of the pipeline is to have a pixel-based PSF model. And if the model cannot represent the ground truth wavefront error, the lowest error on the wavefront error is not necessarily the most useful pixel PSF. And here is, for example, one interpretation of what's going on here in this estimation. We can have here the wavefront error space, and in this ellipse, we can see an example of what models can be represented by the ground truth model on the PSF field. And here in yellow, for an example of what our model can represent. We have some models that are outside and some models that are inside. And actually, the model that is closest to the ground truth here on the wavefront error space is not necessarily the one that has the lowest pixel error. And if we see some examples of the features estimated by the data-driven part, we can see that there's some structure in these features that are being learned, and that they represent some type of lower dimensional manifold in this wavefront error space, and that they provide a very good pixel error. This is one of the tasks that we wanted to solve, the monochromatic pixel estimation. So estimating the PSF for each single wavelength and at super resolution. And we can see that the relative errors are very low in this plot with the wavelengths on the x-axis. And this is very nice. With the shaded area is the standard deviation over the number of test stars that are on the field of view that are different to the stars used for the training. And it's nice to see that this model is actually not degenerated with respect to wavelengths that could be happening. And we can say now that we are able to model the PSF chromatic variations due to diffraction in this case. So now there's some preparation for Euclid. So we carried out several studies here. For example, how does the impact of the modeling in the wavefront error resolution has? So which resolution we define for the wavefront error? This is a quantity that has not been sampled yet, so it's actually a continuous. So depending on how much resolution size we use, it will have different errors. The impact of stellar SED errors. Before we're considering that the input SED were perfect, and we're used the same to the model to give as input to the model and to generate the data. But it's not the case. In Euclid, we have like a reduced number of SED bands. So we have some binning errors, and this will be estimated from ground-based service. So we have some photometric noise as well. So how does this impact the PSF generation, just the forward model, and how does it impact also the PSF modeling? So taking everything into consideration. And also we can explore some type of SED interpolation to reduce these types of errors. Then we continued using how, if we use more exposures, as the telescope is very stable, we can use more exposures to estimate the PSF model, and how does this increasing the number of stars contributes to the performance of the model. Then if we can include an imperfect optical prior into the model, trying to include optical information from different sources that we will have available. And finally, how if we can improve the wave diff optimization procedure in order to tackle a phase retrieval problem that I will describe just after. The first three I'm not going to talk right now, and focus on the last two. So using an optical prior as a parametric model, so we can define some type of prior that is built up with a ground truth and some type of error. So this prior can be very complex complementary information that come from different sources, normally optic information. Here I'm going to use some simulations because I don't have access to the other ones yet, but for Euclid there will be. And actually the output from the parametric model can be one of the input of the sources. So this will be built with a ground truth and some error that will come from measurement or modeling, depending on which source of prior we are considering. I'm going to use this imperfect information into the model. That is very simple because we are in the wavefront error space, and it's very simple to model things in this space. And we can add them directly here. Normally this information comes directly as a wavefront error information. We're going to build our observations with this ground truth, and then we're going to feed the model with the prior that has this error that we don't know. Now we're going to study if using different priors with different errors, we can use it in the model to try to estimate with the observations and this prior a good estimate of this error, and actually estimate the ground truth wavefront error. This is an example of the simulations that we are using. There are Euclid optical simulations. Here you can see the spatial relations of each Zernike polynomial in the field of view. Here just cutting out the 22, but we're up to order 66, so it's very complex information. And this defines the Zernike spatial relations. So now in this case, we're going to focus on the shape metrics. So actually the Euclid requirements for the PSF are defined as terms of ellipticity and the reconstructed ellipticity. So here we're going to focus on these shape metrics. So here you can see in the first part, the first component of the ellipticity, on the second one, the second. On the x-axis, you can see the relative error that we introduced in the prior. So more on the right, the prior that is given to us has more error with respect to the original energy. So you can see here a different how the prior performs by its own, and then how the prior when added to the non-parametric model and added to the parametric model. And we run our model, and we can see these performances that the model is actually very low with priors, to errors in the prior, where here we have a prior doing hundreds of times over the requirements, and during all of the errors in the prior, we are always under 10 times the requirements. Even here, when the prior is very, very good, we are over 3 times the requirement. And it's actually nice to see that in any case, we're always improving with respect to the information that are in the prior. And it has a similar behavior in the second component of the electricity. And now, before ending, we are going to consider a new scenario that I think is very interesting. You can see the model built in the wavefront space, our observation, and what is linking both of them is the forward model that we have explained before. Now we're going to consider another scenario where what happens is the PSF model actually can represent the ground truth wavefront error that before in the previous scenario was not the case. So in this case, this inverse problem has a known minimum that before we didn't have guarantee of a global minimum. And the global minimum right now is the ground truth wavefront error. So in this case, it's actually worth targeting this ground truth wavefront error, and we try to see if we can actually compute it. So actually estimating this minimum is a very hard problem. It's a phase retrieval problem because actually when we're going to the wavefront to the observations, we're just measuring the intensity and we're losing all the phase information. And it's even harder because normally phase retrieval, you have several intensity images of the same complex object, and you use that diversity to estimate the complex information. However, in this case, we just have one intensity image per complex object, but all the complex objects are related to the PSF field. The PSF field gives you the wavefront error at single position, but it changes at different positions, but they are related. So classical phase retrieval methods are not really useful in this setting. Right now, we're not able to estimate the ground truth wavefront error with what I have shown you before, and the errors of the estimating the wavefront error were very high. We're still only using these degraded in-focus observations like this. So we're going to propose a new optimization procedure for tackling this problem. So this new optimization procedure, we're again only going to rely on these in-focus observations. And what we're going to exploit to tackle this problem? Well, the diversity from the wide field spatial variations of the PSF, which constrain the PSF field, and the fact that our knowledge of the PSF field, we have some knowledge of the PSF field structure, because here now our hypothesis is that our parametric model can represent the ground truth. So actually, the ground truth belongs to the models that can be represented by our parametric part, and also from the previous optimization framework. So here you can see a new wavefront error projection method where the data-driven wavefront error part is decomposed into a parametric part that can be reproduced by the parametric model and the residual part. And this is thanks to that the Zernike polynomials are orthogonal in the unit disk. So the new optimization procedure, you want to start optimizing only the data-driven part that has a much smoother landscape, has very over-parameterized part of the model. Then we project this data-driven part onto the parametric part of the model to keep this learned part in the model. At this point, we are in a global minimum, in a local minimum, sorry, and we have to get out of there to continue the optimization. So we're going to reinitialize this data-driven part after the projection and to escape this local minimum. And then we're going to repeat this procedure several times. This is one optimization cycle. And here you can see the performance results that are actually very impressive. We're using only 9 optimization cycles that I described before. We can have a wavefront error root mean square error of 11%. Here you can see the ground truth wavefront error and our estimation, our parametric model estimation, and the convergence, the non-parametric part. And here, both of them. You can see the parametric part of the model and the ground truth are really very close. And we also maintain a very low pixel error. At the end, the drawback is that the computational time has increased. But how much? Well, it's increasing linearly with the number of optimization cycles. We can see here the convergence of the model. How does the wave frontier estimation of the total model goes converging toward the ground truth error as we go to the cycles, and how the non-parametric part of the model goes converging to zero as we go to the optimization cycle. That is very comforting. So here we're right to the conclusions here. So for the data-driven PSF ground-based telescopes, we have built a novel PSF model that is capable of modeling the PSF and the entire focal plane at once. We have validated this with real data from Thesis and then use it to generate a very big weak lensing shape catalog. And in terms of space-based telescopes, we have built a physically motivated data-driven PSF model that has actually a breakthrough in performance and is able to model the PSF chromatic variations in this data-driven scenario. And we have also opened new research directions in the data-driven PSF modeling. So, for example, adding an imperfect optical prior or a new optimization for wave frontier recovery. So, to end some perspective of this thesis, in the ground-based part, we can, for example, consider a deep plug-and-play optical prior for the first model, where we're trying to include this optical characterization of the optics of the telescope into the model. That actually we're completely neglecting this. This is something we obtain from measurements. And then for a space-based telescopes, also there's the non-parametric phase retrieval to try to exploit this new optimization procedure, including some phase diversity observations. So these in focus out of focus images. We can use this wave diff for the James Webb Space Telescope. Actually, real data is going to be coming very soon with the Cosmos Web Survey, and they're trying to do with lensing over there. And also the wave diff for Euclid, where we have some extensions that we should follow in order to guarantee that it's going to be a robust model with real Euclid data, and also including this chromatic dependent of this the correct filter. So I'd like to thank you all for the presentation. I just leave you with this example of PSF reconstruction by the wave diff model.
Thank you very much, Tobias. We'll directly go to the questions by the members of the jury. Maybe we'll start with Gabriel Peyré, who's right here. Maybe actually before we start, maybe we can briefly introduce ourselves to the audience. So what we go through.
So I'm Gabriel Peyré from École Normale Supérieure.
I'm Jason McEwen from UCL in London. I'm Martin Kilbinger here from Cosmologists.
Jean-Luc Starck from Cosmologists.
And then online, start with Andy.
Hi, I'm Andy Taylor from the University of Edinburgh.
Good. And Laure. Julie.
Hi, I'm Laure Blanc-Féraud from CNRS in Sophia Antipolis in France.
Thank you. And Julie.
And hello, everyone. I'm Julie Delon from Université Paris-Cité in Paris.
Thank you very much. And I'm Ben Wandelt from Sorbonne Université at the Institut d'Astrophysique de Paris. Okay, so now let's go to the questions and we'll start with Gabriel.
Thank you, Mr. President. So it's my honor to start. Maybe before I could say a few words about your work and your presentation, because I must say I was really impressed by everything, basically, by your manuscript, which is very impressive. It goes into very fine details. Obviously, it's not really my field or this area of modeling in astrophysics, but I enjoyed a lot. I learned a lot, actually. And also what is more, I would say, on my expertise, which is on optimization, on deep learning, whatever, it was also very sharp. You really go much beyond the state of the art, so the results are really superb. And also your presentation, I must admit, was very clear. It even helped me to re-understand things that was not totally clear, so you really made a nice overview. So that's it for the congratulations, but I wanted just to say the same. For me, it's very important to convey my positivity about all your work. Maybe I can start by some kind of a general picture question about these two parts. So in your work, there are clearly two parts, and difference you clearly split into like cut in two. Could you comment a bit about the integration between the two? Is it like totally disjoint, both in terms of modeling, but also in terms of like practical software? Did you like reboot everything, or is there some part in the software that are actually common?
No, in fact, the first part, of the ground-based models, there was already some developments on our lab, and there I took, for example, all the graph-based constraint was already developed in some other papers that was done for previous PhD students. And there I started from some code that there was already there, but I did all the extension that was quite heavily in the coding part to make it work for all the CCDs and everything. But the new part is really from scratch. I started from a Jupyter notebook, testing stuff, and then it started to build up on a NumPy to test the things, and then on TensorFlow to make sure that the model is working, and try to validate it. I also exchanged it with Pierre-Antoine, that I thank him very much. He's has a lot of knowledge in optics, to validate the model and to make sure that everything, the assumption I was doing were okay. And yeah, it was literally there are two completely different software models, and they have nothing to do.
And in your opinion, there would be no, so maybe if you just first. So on the first part, there is basically no GPU, no differential programming.
No, nothing.
And in your opinion, would there be some interest in like extending this work to integrate like in the same spirit, like having things that would be differentiable first with your GPUs? Would it be interesting? And then would it be interesting to be able to fine tune some parameters through basically random distance?
Yeah. Indeed, I think what it will be the most interesting part is for this part. In the second part, I'm just modeling for now the PSF field in the wavefront space. But there are some contributors to the PSF field that are well modeled in the pixel space. So it will be very interesting through this last part to add some data-driven pixel modeling, and that it should be differentiable to make continue all this work. Because actually, if you want to model here, our simulations are already all modeled in the wavefront space, and there's no some type of detector level effects or some pixel errors, some type of errors that are well described as a convolution in the pixel space. And it will be very interesting to adapt something of the other model or some other type of appropriate thing as a data-driven pixel part in the second model. But of course, will be interesting on the first part as well.
And on this idea of like switching to like TensorFlow or whatever deep learning pipeline, in your opinion, what was the key? What made you switch to this? Is it because you wanted to go to GPU, or is it really because it was very practical to do like the black Hoffman?
Actually, it
could be both. It could be both.
It can be both, but actually it was very practical to have the gradients. Actually, once we have the things implemented, it's very easy to add some, for example, modify the loss function and have all the gradients propagated. I could like test different regularizations of the problem that actually I didn't mention at all because they were not working very good, but it's very easy to develop, and also it's a very hard problem. And there's actually some line of research. There was actually in a summer school where there was some line of research from people working in some optical companies trying to using automatic differentiation to tackle some the designing of optical systems through this automatic differentiation. So they simulate a forward model with all the optics, and then there are some parameters defining this model, and they try to optimize with respect to them. And they were having some nice results on totally different problems, but actually that's motivated me also to go to using automatic differentiation part.
And so would you say that the astrophysics community has switched to differentiable programming? In your opinion, would people now in astrophysics, maybe in optics for astrophysics, really consider like coding everything in Python, or is it like just a minority that would switch?
I think it's starting to change a little bit. For example, there are some efforts trying to build some differentiable parts, some differentiable not only models but some differential analysis in the astrophysics communities. For example, there's one of the researchers in our lab is really pushing that forward. That is François Lanus, and there's many advantages of having the gradients. Even if you want to do inference, having the gradients of your likelihood and your forward model is very useful. You can accelerate the different inference techniques. and I think it's nice. It all takes some time to code in these frameworks, but and not everything can be coded because there are some like really dense programming that is has to be emulated maybe, but I think it's very useful, and I think that the community is starting to switch a little bit. You cannot do anything but everything, but there's some change over that direction.
So yes, my question, my next question is, are there some primitives that are currently lacking in usual PyTorch, traditional deep learning pipeline that would be needed to be added, like recoded in CUDA or stuff like this, or is it like everything is already there?
So I think depending on the application, but just to mention one that was a project from another postdoc in our lab that he needed, for example, in order to do his project where he was trying to do some type of meta calibration using automatic differentiation. So how to try to calibrate this shape measurement using automatic differentiation. He needed, for example, a kinetic interpolation kernel that actually there's no one in TensorFlow and stuff. And he had to put a huge amount of effort to code it in CUDA and make it work, and all the compilation stuff going on. Luckily, in my work, I could adapt stuff that were already there and didn't have to touch any type of CUDA at this.
So you didn't need to implement by yourself some Jacobian vector?
No, luckily no. I was able to readapt stuff, and also the community has developed a lot of, for example, these TensorFlow add-ons, and luckily enough, I didn't have to re-implement stuff from the ground, at least in CUDA.
Okay, maybe just a last point where you mentioned optimal transport. That's important.
Yeah.
So maybe a naive question, and as you would see, I'm really very bad at optics, but it's obvious that the kernel has to be positive. I mean, because it's like from the physics.
Yeah, in fact,
has to be positive.
Yeah, right? In the last, for example, because you're propagating this wavefront error to the pixel plane, and at the end, what you're measuring is the intensity. So at the end, you kind of can simulate this propagation with the Fraunhofer approximation. You can do it using the Fourier transform. At the end, when you have your wavefront at the focal plane, you just measure the intensity. So actually, it's a square modulus of this stuff. That's why you lose the phase, but it actually makes your things positive. But actually, one thing nice of this last work is that I don't even have to impose this positive of the PSF, because it's actually naturally imposed by the forward model. Because the way it can only give me a positive PSFs.
And would it still make sense because you say optimal transport seems to don't have like percolated to phase modeling, which is fine for me. But is there still some hope to have some kind of geometric models to maybe not optimal transport, but maybe something more fancy? Maybe not even for the solver, but just to evaluate the performance. And does it make sense that there is still a future for a geometric method?
I think so, but they have to be like especially in some places in the model. In this case, what they tried to tackle with, I think, optimal transport was too ambitious to model all the spectral variations of the PSF. But for example, there are some other problems at some points that can be easier to model. I'm thinking right now of the dichroic, the problem in the dichroic. That is, this was the one component in the telescope that introduces some spurious variations. And if you see the curves of how does this changes through the field of view, they really look something similar to when you do some displacement interpolation of some curves in optimal transport.
And you have some physical reason for this, or is just like the observation?
So the physical reason of why they are like that, I think, is just due to the characteristics of the system, because you cannot have like you have this physical system, and as you change on the field of view, you are changing your angle of incidence, and this makes the change be very smooth, but in some strange ways.
Okay, that's interesting.
But yeah, I haven't explored it yet. But
okay, thanks a lot. I will stop here, and once again, congratulations for the beautiful work.
Thank you, Gabriel.
Thank you, Gabriel. Next, we'll have Jason.
Thanks, Tobias, for a fantastic talk. I'd just like to echo some of the comments made by Gabriel. That it's really very impressive work. It's rare to see such interdisciplinary work, and I would say, you've gone more than just beyond two fields here. You're crossing, multiple fields from cosmology to optics to inverse problems. So it's really truly interdisciplinary work, and I think as you demonstrate, the deep kind of coupling between these areas has led you to, a breakthrough in performance really in these methods. So it's very impressive work and very clear presentation and very clearly described in the thesis as well. So with that said, I do have some further questions as well. I was wondering if you could maybe talk about this kind of interdisciplinary or multidisciplinary approach here. I guess machine learning has become very prevalent in recent years and has had a great impact. But in many cases, it's applied kind of picking up machine learning techniques and applying it to a given problem. Whereas here, you've really integrated the physics and the learning kind of component together, which I would say is one of the reasons that's led to this dramatic improvement in performance. So I'm wondering if you could look, beyond just your work and see, how do you see these fields evolving, the interplay between machine learning and physics? Are there things you can say about that more generally?
Yeah. So to talk a little bit about that. So I think like machine learning is going to have a role in the following years and going to be maintained. But the way maybe you used it is going to change a little bit. So actually it has to be very constrained on what fact is going to have to be useful in the places where we don't know some things, or we have to like model some specific, for example, some mapping of some functional to some other functional. Here in this example, it wouldn't make sense to model as a wave at some point I thought about it, just using a neural network, for example, to emulate this propagation. Well, it doesn't make any sense because actually we know the optics and we know this, we can actually build this forward model. But for example, it would make maybe it may be useful, for example, to have this here I'm modeling through matrix factorization, but to model it in the wave vector space directly there using this forward model. The why I haven't done that is because I really required some guarantees that the model is really has some smoothness and that it really can be applied. And if I introduce a position that I have not seen during the training, I really need that the model need to be very robust in this case. But I think it's going to have a play. There are several use cases of machine learning that's very useful. Even like for the training of the model, I'm really like, I just robbed some of the machine learning techniques and was very useful. Like at the end, even though I don't have any type of neural network here, it was optimizing a non-convex and a very high dimensional function, very fine. And yeah, I think I'm just talking too much.
So but coming back to the MCCD approach, sorry, and in fact, maybe this is in wave diff as well, but you consider a denoising component of the problem as well, where you impose some kind of sparsity. And I think in simulations it worked fairly well, but then when it came to real data, you were sometimes seeing artifacts. So I was wondering if you could comment on that any further. Is it necessary to have this denoising, or maybe it's fine without it? Or are there other ways you could try and deal with this or introduce this?
Yeah, so actually that's a pretty good question, because actually the denoising on these models is pretty particular. So if you look on the literature, there's no model doing denoising. All of the other PSF models are not doing denoising. Why? Because in fact they're not had to use a denoiser; they're just implicitly denoising by using some type of low rank in the model. So by reducing the number of features, for example, you're imposing some type of denoising without having to use a proper denoiser. When the model, you're trying to build bigger models that can model more complex type of variations, you're interested in building some type of denoiser, because at the end, if the model is very complex and start learning some noise and overfitting to some data. So you need some type of regularization when you increase the number of models. However, it has to be very careful, this denoising. What I've learned here, and at the end, what experience showed us is like, for example, what was I was using for denoising? I was using some type of wavelet decomposition on some wavelets that are called starlets, they're isotropic. So this decomposition is isotropic. At the end, what I saw when working with real data, that the ellipticity variations were small, and you have to have very accurate modeling, is that this isotropic denoising was biasing my model towards more round things. So you could directly see it when you measure after many stars. this denoising on isotropic wavelets were biasing the model towards rounder objects. So you could directly see on these main shapes where you see that, for example, for everything had a bias towards 0, because for more round stuff. And actually, as we're in that case, we're really interested on having the minimum bias possible, not having the most denoised model as we wanted. We ended up using no denoising because before we didn't have any more sophisticated technique that could overcase that. So that's why at the end we didn't use denoising, and why in the simulations it was working better, because the variations of the electricity were much stronger than the ones from the real data. The real data were very, very small, and you need to be very fine. In that case, like denoising, you could see it very clearly.
And so do you think going forward, there's no need to denoise it? It's better to actually just make sure you fully understand, you eliminate bias, and then you can model everything it's accounted for? Or do you think maybe there's still a future for trying to?
Well, it depends actually what are you trying to model. So if you're trying to use a very simple model, there's no need to add any type of denoising, because already the model is already being kind of naturally denoised, and you're trying to model something, a simple variation. But if you really need to push it further and model more complex type of variations, you will need to have some type of denoising, and in that case you will have to define one of a denoiser that's actually driving you towards what you want to be modeled. For example, that's why one of the perspectives there, that the idea is to build a denoiser that doesn't bias you towards a round shape, but bias towards this pattern that you're observing, that's actually trying to introduce this information into the model.
Mm-hmm. And so I guess, yeah, when you're doing that denoising, and if there is some residual bias, you're not kind of capturing that uncertainty. So as you've suggested, you can either not do it, or maybe future methods where you can address that. I guess, you know, at the moment also you come up with one kind of estimate of the PSF, like a point estimate basically. Yeah. So do you have any thoughts on how you could try and characterize the errors or the uncertainties in that estimate?
Yeah. So yeah, for the first model, it's going to be I think harder. The second one, we have our gradients over there that we can use and exploit. And you can think of trying to build some type of, to do it on more a Bayesian framework. Actually, what we are estimating on the second model is just the kind of the posterior mean. But you can try to build some probabilistic inference of the model. It's very high dimensional, so it has to be something very simple. For example, each parameter is going to be kind of a Gaussian, and then tackling it through some type of variational inference, where we're trying to estimate these parameters of the model. But I think that's one way to do uncertainty quantification on the PSF model. However, there's another question, that is, do we need to do this uncertainty quantification in the PSF model? Because at the end, what we are interested is in having uncertainty quantification in the shape estimation. So it will be more interesting to develop a method to propagate the errors in the PSF model to the shape estimation method, and then estimating how does this error compare to other errors, and how can this error be reduced for the task that the PSF model is being used for, and not directly for the PSF model itself. Because that was one of the things I kind of learned using real data, that you can have you can define some metrics for your PSF model, and you can optimize this metric for your PSF model, but at the end, the metrics that you're going to use are the metrics with the task you're tackling, that is having a unbiased shape catalog, which is why at the end we turn out the denoising, because even though it was having a lower pixel error in the reconstruction and having a denoised model, it had some bias on the shape catalog that was not what we wanted. We wanted having a lower bias on the shape catalog.
And so maybe, so you also did some experiments to look at the impact of noise or errors on the input. So for example, on the Z profile, and there you found your method to be very robust to the noise. In fact, in some cases, it even gave better performance when the noise increased. Do you have any idea, like intuitively, why is it so robust to noise? And is it like, why might it get even better with more noise, or is that just a statistical fluke?
So why it is more robust? I think because this SED that I was using, so the stellar SEDs, so SEDs from the stars, are much simpler than the galactic SEDs. And these stellar SEDs, if you look them, okay, they have some variations and some absorption peaks that they are very thin, and mostly it's a very smooth curve that actually using very small, very limited number of samples, you can approximate it quite well. And actually, that was some things that we saw that even using a very small number of beans compared to using all the beans that a very high discretization, we found very little error between both of them. So I think that's one why the model is quite robust. Then why the model was giving sometimes better performance with errors in the SED. That is, I don't really know. It was I think it's just the variation of the performance in the model, or I haven't looked for it in detail.
No, but it's very pleasing to see it's very robust to that uncertainty in the input. Just one final question. So it's very impressive, this extension to the wave diff approach at the end that you presented, where now you do the space retrieval problem and you recover this wavefront surface. I mean, as you actually mentioned in your talk, for the purpose of weak lensing science, actually what is critical is the error at the in the pixel domain. Nevertheless, you know, it's fantastic to see that it's actually possible to recover that wavefront error, but at the moment, you're not making use of that any further. So I was wondering if you had thoughts for how these kind of techniques could be put to practical use, or maybe the use of them in other areas as well.
Yeah, so actually it's very interesting because recovering this ground truth wavefront error, even though it's not what you're going to use later, it actually gives you a physical representation of what's happening on the telescope. So actually, if you can actually estimate this from these fields, you can actually see if there is some problem in some part of the telescope that can actually be very helpful later. And also, okay, it takes much more time than the original method, but you could, for example, run this one or a couple of times in some very dense stellar field, and then use that as an input for the models that are going to use later, right? As it will be the prior later, which will be like very helpful. And also, you still have to push it forward to see all the potential. So like using that on a more realistic case, for example, I haven't done yet, mixing the last two studies that I've shown, for example, using this prior and using this type of wavefront recovery to see if actually with using this prior, and this new optimization technique, I am able to literally estimate this delta error function, delta error from this input information. And that will be actually very helpful.
Great, thanks.
You're welcome.
Thank you, Jason. Now let's go online. So we'll start with Julie Delon.
Hi, can you hear me?
Yes.
Okay. So, Tobias, congratulations. It's really, really an impressive work. I learned a lot, like Gabriel. I knew not much about cosmology, and it was really interesting to read your manuscript. And okay, so I have a few questions that have already been posed, but there are some still remaining. So my first question is about the noise model that you consider in your manuscript and in your work. So if I understand well, each time the noise model is Gaussian, is an additive and Gaussian. That's true, or?
Yes, indeed.
Yes.
Yes.
And okay. I know nothing about astronomy and stars, but I always understood that it was low light imaging. So shouldn't Gaussian noise model not be very accurate for this kind of images?
So actually, if we observe so wait, I have some problem with the screen sharing, and then I'll try to ask you. Sorry for this. Okay, well, let me answer you. So, in fact, I haven't got yet Euclid observations, but from the surface observations, the noise is actually very close to Gaussian noise, and we know that there's going to be some type of some type of Poisson noise,
Mhm.
but actually we're kind of neglecting that for the moment. But we could adapt our loss functions to try to take that into consideration. But yeah, indeed, it was. I think at the end the noise will be close to a Gaussian, but not necessarily Gaussian. But yeah, that will be like need to be studied. I don't really know exactly the statistics of the noise from the Euclid survey, but at least in Thesis, it's very close to a Gaussian, and it's working fine with this assumption of having a Gaussian noise in our observations.
Okay, okay. And what is the dynamic range of your images? Is it 12 bits or?
Good question. No, I don't
Because
remember. From the Euclid observations, I'm just making my own simulations.
Mhm.
So I'm just using the default NumPy float precision.
Mhm.
But for Cephis, I don't really remember, to be honest.
Yes, I assume that it's an important point, the quantization level of the images sent by the telescope.
Yeah, but I really don't remember right now the dynamic.
Okay. So,
but it was not having any type of issues with this. Actually, it was pretty controlled in the. So actually, in this processing pipeline, there is already some pre-processing of the images.
Mhm.
So actually, sometimes there are some instrumental effects that, for example, correlate the noise, and sometimes it's decorrelated. So this assumption of white noise is kind of maintained. But and now I don't remember about the dynamic range. But
okay.
I had no problem with that. I didn't found no problem with that.
Yes, because I thought that it's also a source of uncertainty in your results. So you take into account perfectly the spatial resolution, but you don't speak about the gray level resolution, or I don't know how to say it, but well, okay. So you answer me. It's still about noise. You have really interesting results where you show residual maps in your part on multi-CCD, your multi-CCD PSF model, your ground-based telescope. And I was wondering, so these residual maps are still not zero, of course. So I was wondering if you thought about taking into account these residual maps in the functional that you try to minimize, for instance. You could try to add an additive term saying that you want your residual to be Gaussian, for instance.
Yeah, so actually that's a good observation. So we have those residuals, and one difficulty is that to compute those residuals,
Mhm.
you have to compute a lot of stars.
Mhm.
So we can plot. We found these plots after the 3 months computations in this Canada supercomputer.
Okay.
So it's hard to test it because if you just don't use such a big area, you cannot see them because it's very noisy. In fact, the more observations you do, is like the more spatial resolution you can do there, and you can see these systematic contributions, and actually very close. So yeah, I thought about that. I haven't had the time, honestly, because once we define the model and we run the data, you obtain the catalog, and I continue working in Euclid. And but it's actually something that is, I think, the next thing to take into consideration for this ground-based telescope is try to how can you capture these very small spatial variations that were actually not captured by the model. And I think one of the things I learned by working in that is like you cannot directly learn them from the observations on their own because you don't have enough information. So the stars are so sparsely distributed on the field of view that you don't have enough samples in order to capture this variation. So that was one of the ideas that I had of the perspective to try to capture this variation on the try to introduce it into the model, because otherwise that is something. What you mentioned, I think, is another approach of trying to introduce these residuals or these type of variations into the model.
Okay, that makes sense. Thank you. I had a question about when I started to read your thesis. I was wondering if it would make sense to take advantage of a multi-image framework, and you say a bit about that in your manuscript, and it was also in your perspective slide, I think. And could you say a bit more about this possibility? Because I don't understand what would be the difficulties and the limitations of doing that.
Okay, with multi-image, you mean to using several exposures?
Yes, exactly.
Okay, then we go to I go to perspective.
What we do classically in photography, but I assume that it's much more difficult with your images.
Yes, so let me go to perspective and I'll answer.
Yes. My next question would be also about perspective, so you can put the slide.
It's getting hard.
You're too fast.
Yeah. Okay. So yes, so the question about the multi-exposure things. It depends if you're considering a ground-based telescope or a space-based telescope. Why? Because in the ground-based telescope, the atmosphere belongs to the PSF model. So actually, when you're modeling the optical system, the atmosphere it's also part of the optical model. And each exposure, the PSF is changing. So if you, for example, you would like to, for example, try to use several exposures of the same object to improve the signal to noise ratio, for example. However, if you do this and you try to model the PSF on this new image, it's not going to be well defined depending on this coaddition scheme that you use. There's actually a very recent paper of a group in the US working also with weak lensing that they, in order to have this convolutional property of the PSF in a co-added image, so using several images to add to produce a new image, there's only one or two ways. So it has to be linear or some other very simple approaches for this coaddition to have a well-defined PSF. But then these very simple coaddition schemes have other problems. So actually, it depends. It depends if you want to model the PSF. I think for in a ground-based part, what it would be best is to use each exposure. But if you want to do some other task, for example, detecting something, in that case, you're interested in the PSF and you would like to stack images together to improve the signal to noise ratio and detect things that are pretty deep. But if you want to model the PSF, if you do this, then the PSF might not be well defined. And with well defined, I mean that the objects are the underlying object convolved with some PSF kernel.
Okay.
For space-based, sorry, just one thing. For space-based, the telescope might be very stable and you don't have the atmosphere, so you can actually exploit different exposures to use this, because the telescope is very stable and the PSF you can assume that it's not changing between one exposure and the next one.
Okay. So in the ground-based case, it's only because of atmosphere that it will change too much between two exposures?
Yeah, because the thing of the atmosphere is that it changes very fast with respect to these exposures.
Okay.
In the space-based, it's also changing in time, but the changes are very slow with respect to
its temperature.
Yeah, it's mostly driven by the temperature gradients that make changes on the mechanical part of the optical system.
That's really interesting. Okay, thank you. Maybe a last question. Yes, Jason, one of my main questions was about the Bayesian interpretation of your work, and would it be possible to reinterpret it as in a Bayesian model? And Jason asked also something similar. So maybe just to relate with one your perspective, you speak about deep plug and play optical prior for MCCD. So it would be a way to in a plug and play framework, you can always put it in a Bayesian framework and then do Bayesian analysis. So is that among the possible plans, and do you have precise ideas of how to do it?
Yes, indeed, I have maybe a slide to show because we started working with that.
Ah, excellent.
Yeah, you can see the slide, right? Okay. So in fact, the idea you can do. So we haven't finished the work, so actually that's why I haven't shown it. But the idea is like to capture these very thin variations of these ellipticity variations. Try to introduce this into a model, and we are trying to introduce this using a denoiser. Of course, this can be built in a vision framework. It has not yet been finished, but this is the main idea of the method. How can we inject this as a prior? Okay, using the denoiser, and for that we have to build. Okay, we have many simulations, following these patterns on top of the simulated atmospherical pattern, and then we just with a very dense stellar field. So we have a lot of stars, so we can actually, it's so dense that we can actually estimate these very thin variations. And then these features or IGMPSF that I call here of the model are actually modeling these very thin patterns. And actually you can use these learned features to train some denoisers in order to denoise these type of features, because at the end the denoisers is acting on the features. So once this denoiser is going to be biased towards these training samples that are the training samples that are actually able to represent what we want to represent, and this will be and once we have trained this denoiser over these simulated these features, we can try to inject this denoiser into the model, replacing this wavelet denoising scheme by this deep learning denoiser. And then the denoiser will be inside this proximal operator in this optimization algorithm. Will act as a proximal operator.
Okay. Okay, thanks a lot, Tobias, for your answers.
Thank you.
Thank you. And now we'll go to Laure Blanc-Féraud.
Okay, thank you. Is it okay? Do you hear me?
Yes, thank you.
Okay, thank you. So first, I would like to say that you have made, you did a great piece of work, and it was really a pleasure to read it, because it's a very complex domain. I'm not specialist also, but it was really a pleasure to read your manuscript and to see your presentation. So good work. Yes, several questions have already asked, and so let's go to very standard question, as when we don't okay, it was a joke. Hyperparameter, convergence, and CPU time. Okay, more seriously, I was wondering about your algorithm in the second part, in the space telescope. You have a lot of parameters in the model, in the algorithm. So is it a prop? So you show very good results and so on, but we know that making this algorithm is not always easy. And so my question is that, is it, okay, easy convergence? Do you have to fix precisely parameters of the algorithm, of the model, and so on? Because you've got a lot.
Yeah. So there's, for example, there are some parameters that are the parameters of the optical forward model. And those ones depend on the telescope parameters. So depending on the telescope you're going to model. So in this case, it's Euclid. So I took Euclid parameters and fixed them, and that's enough. So they would correspond to what you want to model. Then you have some hyperparameters of the model. For example, how many data-driven features are you going to use? which degree of spatial polynomials are you want to model.
Exact. Yeah.
So like that, and then other parameters on the optimization algorithm that are, for example, the learning rates you're going to use, or the number of epochs that you're going to use for training. So to answer the question is actually the model luckily is pretty robust to this change of parameters. The only thing you have to make sure is that you have enough epochs for the model to converge, because the factor is not has not converged enough. You can see that the performance degrades quite fast. So this can be easily seen on the, if you plot the loss as a function of the epochs, you can see when it has kind of converged, and you can, in this case, I was kind of trying to push it for performance and not necessarily for the time. So I did some more of epochs to make sure it has converged. And then in in this last method, in order to the convergence, if the learning rate is small enough, so it's not very big, it always in what I have seen is it always converges to some type of local minima that can be better or worse, but normally they're all of them having a good pixel representation error. But if you, for example, if you allow the learning rate to be pretty big, you can like converge in a model that it's kind of nonsense. So at the end, to conclude all this answer, the model is actually quite once you more or less once I set up the parameters for how many epochs I needed to converge, which was the learning rate that was kind of good and not too big but not too small, so it's not that slow. Actually, I don't really need to touch them much more. Well, actually, what I can change is making the model a little bit more complex or less complex, but the optimization part and the forward modeling part is already kind of fixed.
Okay, so when you go to further new data, then you have the right algorithm. You don't have to run it again a lot to fix parameters.
Well, it depends how much the real data will look like my observations, my simulations. If they are kind of similar, I don't expect it.
Okay.
But if they change, we have to validate it.
Okay. And then with respect to the CPU time, the question is, what's in absolute is yes, is it very time consuming and so on? Okay, it's a question that I would like an answer, but the question is more like that. When you will be in the process, when you will have several data coming, will it be possible will it be incremental in the sort that you first estimate PSF in part of the sky, and then maybe you can use this knowledge for other observation, or how will it work?
So I think the precision required in Euclid makes you to estimate the PSF model for each exposure. So you cannot bypass the need for estimating on each exposure. But what you can do is have a very long estimation for one field of view that have a good conditions, and then try to use what you estimated there to use it in another fields as the prior here, for example. But I don't think you can actually bypass the need for a proper estimation of the telescope, because actually the requirements, as we have seen during the talk, are very low. And even though that we had a prior and we're doing a lot of several epochs and taking our time to estimate the model and everything, we're never under the requirements. But we managed to decrease it quite a lot. But actually, we're still not over the requirements.
Okay. Now, with respect to your perspective part, you still optimize a non-convex function, okay? If I well understood. And there's no perspective on that, I don't know, initialization, algorithm for non-convex estimator, or okay, there's no, it is not a problem.
Well, it actually is a problem, but so you would like to have a better optimization algorithm?
I don't know. That's the question.
It's a
Why do you use Adam?
because actually,
Oh, it's very important.
yeah. So just Gabriel asked why I was using Adam.
Yeah.
It's actually always converging to a useful local minima. So a local minima with a very good. It was converging fast, and it was giving a good convergence to a local minima with a low pixel error. So it was very useful and at the end you can see on the features that you have some type of, it's not just noise or
Actually, using stochastic rather than this.
yeah.
Because it's too large scale. So
Yeah. Thing is, like, you have a lot of parameters, and you can see that each observation is 32 by 32, and the feature is 256, 256.
and it works with SGD.
So actually, what I haven't tried too much SGD. I started with Adam, was giving very good results. Then I switched to rectified Adam because actually it worked better at the first with the difference. This estimation change in rectified Adam was more stable. But I think I haven't done a very deep study on changing to SGD. But I think actually Adam was working very fine and was converging very fast. So I kind of stick to it. But it's true I haven't properly studied directly SGD.
Okay, and on the slide like we see, so you propose to use a plug and play algorithm for denoising, and I was wondering, is it a choice? Do you have reason to consider this approach? I mean, there's denoisers using generative neural network, which also works well as a variational autoencoder with denoising or GAN. And so the question is it because, yes, it's just like that, or do you have a reason for using the plug and play approach? A specific reason?
Yeah, actually, because it fitted very well to our framework. So we have all the optimization algorithm that is already built with this block coordinate descent, some proximal algorithms, and it's very good to the framework, such that it was acting as a proximal operator in all this big optimization framework. So it actually helped us to solve the problem of denoising and the problem of this of including this information and for the other bias in the denoising. And I think what drove the choice was mostly the framework in which was going to be used, and also it's pretty, as the framework is already pretty solid and it's not right now there's no type of neural network, and it's everything is kind of well studied, we can say. Using this type of denoiser that has maybe less guarantee, but can be more unstable than a wavelet denoising in this like constrained framework, I thought it was a good choice.
Okay, so thank you very much for the discussion. Thank you.
Good. So thanks, Laure. And now finally, we'll have Andy Taylor.
Hi there, thanks. Thanks, Tobias. That was a really nice overview of the work. And I think, like the other examiners, congratulations on a very nice thesis. It was a real pleasure reading through it. It's also, I think, you're tackling what is a very difficult problem with the PSFs for these surveys, but also a very critical one for them, as you've outlined. We've got to get those images and wavelength dependence right. So, it's a major undertaking, but I'm glad someone's giving a lot of thought about how to do this properly. I was going to really start with maybe more of a general question. You've now sort of immersed yourself in the world of PSFs for a few years now. So what do you consider being the major challenges for PSF analysis for weak lensing surveys?
Okay, so actually one of the biggest challenges is the requirements that are set for Euclid that are extremely low.
Mm-hmm.
And there are also several effects. So I think I may make a small critique here is that the requirements are defined on these ellipticity measures. That actually the ellipticity at the end is used kind of as a descriptor of these shapes. And when you are in ground-based service, it's fine because everything is close to a Gaussian, where you're actually in a Gaussian, you're perfectly describing the shape with ellipticity and the size. that if you're going to space and you have to observe these diffraction limited PSF that have very strange shapes, actually then the ellipticity is not at all describing that well the shapes. And the fact that the error propagation, the requirements are set in ellipticity, I think it's not the best choice. And it's very hard to comply with these requirements, even if it's possible to do it with these types of requirements in ellipticity. That's why I haven't shown that much the errors in terms of ellipticity, but more in terms of pixel. And also there are some other stuff that is very hard, not only the very low requirements, but also some effects I haven't yet considered. For example, these decorative effects. The decorative effect is actually very complex. That is actually the last part, and you can see there, because it's introduced a spurious wavelength depending. Well, I have some plots to show you, to illustrate it. That is, I think, is very illustrative. Here you can see, for example, how does the contribution in wavefront as a function of wavelength on the x-axis and how much it contributes and how much it changes on each for each Zernike. For example, for the first Zernike, so it's a very big, very different type of variation. So very big, so very like a complex signal. And here's, for example, for the first component. Then if we continue to have some other component with a little bit less energy, but still a lot of energy. And this is how they impact this dichroic on the wavefront error. And in fact, it's even harder, because if we look here, for one Zernike, if we change in the field of view, before it was for a single position in the field of view, how did it change spectrally? Here you can see how this spectral change, it changes over if you move over one line in the field of view. So it's actually changing spatially, spectrally, and what is a pity is that this change, you cannot decompose it into a spectral and a spatial change, but there's like really one function that depends on both of the three, so you cannot decompose it into separate functions. So actually knowing how much this is going to impact and how it relates with other types of error is, I think, it's a pretty difficult question to answer. And if it's going to dominate and how much this is going to contribute or not to the PSF. And I think that's a pretty hard question that needs to be addressed, but I haven't done yet.
No, it's interesting to see those figures. Yeah, and I completely sympathize with your comments about the requirements we set on Euclid. Of course, you know, this is trying to take an engineering approach, and sometimes these requirements don't fully capture what you would like to capture, but it's then set very stringent numbers that we have to meet. So it does represent a huge challenge. And I think you've made great progress here in demonstrating the methods you've been applying, making good progress there. From my point of view, I mean, of course, again, as you highlighted, we made a choice. And again, these choices were made early on that we would pursue a parametric model fitting approach to this. Now, again, you know, things move forward. So again, I'm very pleased that, you know, you're taking up the challenge and looking at alternative ways, because again, you know, by no means do we think we found the perfect way or even the best way. So it's interesting to see these other methods being developed. But I also think they probably got a very important role. And I think, again, you've sort of highlighted this with a method that combines both parametric and non-parametric contributions. From my perspective, I'm interested because we probably know we're not going to capture everything with a parametric model. We have measurements of the optical element's surface errors, but they're only measured at points. And of course, we can't say what's happening on scales below the sampling of those points. As you've highlighted, for the dichroic, we'll get measurements in the lab from a flight spare, which is manufactured the same way as the flight model, but it's not the flight model. So we'll learn something, but it's not clear about how we'll move that information across to the actual flight. And some of the SEDs, you know, we won't have full data for the SEDs. So my question kind of is, in your modeling with both parametric and non-parametric, do you have a feel for how they're contributing? As I said, in my mind, I can kind of understand the parametric is getting the gross features right, and then the non-parametric is filling the detail. But is that how you see it, or do you see it somewhat differently?
No, I see it like in a similar way. So you have the parametric model that can be better or worse. Like for example, in the first experiences I had a very bad parametric model, and then for example in the prior, the parametric model was like closer or more far away from the ground truth. But at the end, what I see is that the data-driven part has so many parameters, because I'm actually estimating each point in this wavefront error features, that it's actually very flexible to adapt and to really have a good representation of the observations. And actually, it's like it will convert the algorithm, it will convert to something that have a very low error in the pixel space. And the fact that at the end the variations that I impose are quite smooth guarantees some type of a very robust like generalization to other positions, right? Was why at the end, like very simple polynomials were for the data-driven part were giving like such good results, because they were actually these very smooth variations of the features were guaranteeing this good generalization of the PSF to positions that were not observed.
Mm-hmm. Okay. At the end, you showed, I think, some sort of a final summary slide, which I thought I was going to refer to, but it's really to do with your, again, looking at wave diff, that as you've highlighted, you get good recovery in pixel space. But certainly one of the slides, that there looked to be sort of a residual wavefront error, which is almost a constant across the field. Now, again, in my head, I guess I, think of these as being Fourier complements, the wavefront space and the pixel space. So I'm just wondering, that's exactly it. Thanks very much. Yeah. So it's really that bottom set of figures there with the wavefront error reconstruction.
Yeah.
So on the left-hand side, you've got the ground truth, you've got your reconstruction, and then the residuals. And again, you've perfectly well highlighted this yourself in both the thesis and your talk. But you're left with sort of what looks like a constant offset or something, which is then in the residuals. So again, in my head, if I think of these as Fourier complements, I'm guessing that may correspond to certain pixels where the recovery is poor. Is that the right way of thinking about it? And because again, your summary was that it didn't really affect the pixel space, but if it's more localized in the pixel space, maybe that's why it's not such a big deal for you. But again, do you understand why is it producing this? Why are you getting these offset in the wavefront recovery?
So yeah, just to mention here, because you can see maybe like very so this actually the error, the color scale here are quite big for the actually ground truth. That's why you see like a little bit fainter.
Mm-hmm.
But normally, because the estimation is much higher. So to answer why this estimation is pretty bad. So in fact, at some point, something that was interesting that I hadn't mentioned in the thesis was one paragraph, so it was pretty hidden over there. There was some experiments I did, for example, trying to put some constraints in this model, but constraints in the wavefront error space. And for example, okay, you're trying to estimate a wavefront error model, and what you want to ask for this model, okay, for example, you could put a L2 penalization in order to prefer models that are less aberrated, which actually makes sense in the physical point of view, because we are not expecting a big a model with a lot of aberrations, or it's actually a very good optical system, the one of Euclid. So, but actually what this did was, okay, we were closer in the wavefront error space. We passed from 120% error to 80 or 70. But in the pixel space, we're doing like kind of almost double the error that we were doing before. So that was a little bit what pushed me to understand this interpretation that's saying, okay, I prefer to have no constraints at all in the features of the wavefront error to be the one that the model converges over there. And this one, I'm sure that the algorithm is converging to this very good pixel representation. Yeah. I'm not sure if that answered the question.
Yeah, no, that makes some, that kind of moves it forward, I think. Yeah. Okay, I think just moving on. I mean, again, your results were very impressive. I mean, in terms of the data-driven method, you've made huge strides, and now introducing effects where you can get the chromatic effects in as well. These are really important for projects like Euclid, and really nice to see now in these methods. Overall, I mean, I said, even though you're getting there, you're still finding some differences compared to what we said as Euclid requirements. So what in your view is needed for this kind of approach to kind of break that threshold? Is it you need stronger priors, more data brought in, or is there a methodological kind of breakthrough that's needed here? What do you see as a way to progress there?
Yeah, that's a good question. I think before answering that question, I should do a study, because at the end I did some studies, like considering some of the more realistic setup, for example, these errors in the CDs, in the input CDs, or this difference between the wavefront error sampling and using more or less stars. So at the end, I haven't done a study where I included all of the effects, having the more realistic setup that I can, include some optical information to the model, and see how our performance is there. So if you ask me, I did like independent studies to have, for example, to understand how much each one is affecting the model, but I haven't done one that comprises all of them. So that, I think that should be done before answering the question. So in order to have, okay, now that we considered everything, so a very realistic setup, all the sampling, different the SCDs, the problems with the SCDs, the more complex model with this prior. And once you have that, you will find some type of error, and then it will be nice. I think that will be easier to answer this question. I think what actually helped a lot is including this prior into the model, using this information of this complex optical model. For example, here it came from simulation. That's actually, I think that's only was one of the things that actually contributed a lot to improve the performance.
Okay, it's nice. I think maybe my last question now is in an ideal world, how would you move this all forward? Would you like to see this implemented in Euclid?
Yeah, but it's I think it will be very nice, but actually very hard work to implement all this. I'm not sure like what are the requirements in terms of in computations, and what it has to verify, or like which systems has to work on. So I think that exceeds me a little bit, but yeah, for sure I'd be very happy to see this applied to real data from Euclid.
I mean, I think we have sort of 6 years of operations and then 2 more years of wrapping up. So there's a future ahead. I think you're quite right to raise the issue of operations. I didn't ask about the performance because that was asked previously, but actually it's worth keeping in consideration at the moment. The PSF fitting and generation is the bottleneck in our pipeline. So we always knew things like a parametric model fitting would be a slow component, but at the moment it is the limiting component in the pipeline. So it's not unrealistic to think that we'll be looking for and trying to improve methods and build on studies like these. So I think it's interesting to keep this in mind and look for ways forward. But otherwise, I think that's all the questions I think I was going to ask. But thanks.
Thank you.
Thank you, Andy. Okay, so I'll ask a couple of questions before I go to give an opportunity to the thesis advisors to comment as well. We've already had quite a lot of questions, so I'll limit myself to just a couple. Before I do that, let me also echo what has been said before. This is technically very impressive work. And I should also say that you've been very impressive in presenting it, and the thesis is meticulously written and very detailed, of very high quality in my opinion. And should also mention that, of course, having chosen such a relevant and important topic for the thesis, so some mention should also go to the advisors for having guided you in that direction. And as we just heard, it's the bottleneck for Euclid analysis. So I'll ask my first question about a very early slide in your presentation. The model that you wrote down, or at least the model that you considered, I think, for everything in this work, was a linear model where the PSF effects were linear convolutions. Now, could you comment on the extent to which that is accurate, or and maybe implications of potential nonlinearities in the processing chain that could have an impact?
Yeah, it's a good question. Because, for example, right now for example, on the first part or on the second part is always a matrix factorization with some, at the end is some weighted sum of these features. So actually everything is linear over there. But actually in the first part, at the end, like what you're modeling the features are not physically, don't represent anything, just some type of dimensionality reduction technique. And the linear part was working pretty fine. At the end, what the nonlinearity comes on the spatial variations, on the function of the spatial variations. On the second part, something very similar with linear features. So I have not explored yet, like having some type of nonlinear mixing of these features, but something that might be worth to explore. Right now, all the nonlinearities come from how these features change and this function, these weights change. And I was mostly focused on, okay, having these features specializing on this type of variation. That was something from the first part. Okay, you have like imposed some type of variation that you'd like to follow, and this feature will like try to describe that type of variation on the PSF. And that was kind of the main like path that I have been following. But I think it's really interesting to at least try and see if like that actually can like open up more doors in the field. But yeah, I haven't tried it, and I think it will be for sure interesting.
Is there does it make an effect that the stars typically tend to be much brighter than the galaxies, for example, when it comes to the way that the CCDs respond to large or small signal?
So actually right now, before we start the PSF modeling part, we do some star selection. So if not, we don't use any type of stars, use stars that verify certain criteria so that they are actually a good representation of the PSF field. So actually normally this is done in a size magnitude plot, and you identify the stars that change brightness and don't change shade, and put some thresholds over there. Actually, there are some effects occurring, like some what we call detector effects. For example, the brighter, flatter effect that it should be considered. And right now, for example, in this last model, I'm not considering it at all, because I was mostly focused on doing the optical modelization, and there is a pre-processing of the images. For example, they're going to correct for CTI, this charge transfer inefficiency. I'm not now. I don't remember if they're going to work or not on the brighter flatter effect. But normally there's always some type of residual in these corrections, and they have to be addressed. But I haven't done it yet. It's one of the things that should be done.
Okay. Yeah, so should say that I appreciated a lot this your work on building a physical model as part of the inverse problem. I mean, as somebody who myself has worked on differentiable forward models since before it was cool. Before there were automatic differentiation systems, and you're building these things by hand, so I just want to say that I particularly appreciate that, because I think and you show that it's very effective. But I wanted to again go back to the assumptions a little bit. You have this parametric model with the Zernike polynomials. And you're talking about model misspecification, which of course is an important issue. That's why you have the non-parametric part. So it's a very nice setup. But I was wondering what would happen if instead of taking too few or just trying to match exactly the right number of Zernike polynomials that you allow, what if you, since you do have regularization, what if you just crank up the number of Zernike polynomials, just make it very big, and you do have sparsity priors and so forth that might just solve everything automatically.
So
actually,
so I tried at some point, because you have or it's less or it's the same or it's more, right? And I tried it. Okay, you put some more, and what I found when you're trying to optimize over this parametric model, using even though if you use a lot of Zernicke polynomials, and you can actually represent the ground truth, is that the optimization procedure with this parametric polynomial is very degenerate. So it's not like this non-parametric part that you can actually at the end obtain a good pixel representation. When you try to parametric polynomial, normally it gets stuck on a local minimum that is quite bad, and it's very hard to get a good estimation. I think the main reason for that is the fact that you have a very few number of parameters with respect to the non-parametric part, and also that there are some degeneracies with representing the PSF with these Zernicke polynomials. And at the end, like it's not as robust as the other one in estimating. That's why at the last part, we are not even like estimating the parametric part. We're just using the non-parametric part and projecting over the other one. Because when you try to optimize the parametric part, everything goes around, even though if you're using all the same optimization procedure, the fact that you have very little parameters and it's a hard problem, it goes anyway. It's a very bad local minimum.
I mean, from deep learning, we've learned that increasing the number of parameters sometimes can actually help with finding good minima. So maybe you didn't have enough.
Okay.
Even more. Good. The other thing I, of course, liked is that it wasn't purely methodological, even though, of course, for Euclid, there's no data yet, and you had to work with simulations, but that you also looked at applications to real data and got some non-negligible improvement, some tangible improvements on those as well. In this particular case, this may not be that much of a problem, but with deep learning frameworks, when you're using gradients, automatic gradients, sometimes, even though strictly speaking the gradients are exact, but they're sometimes can be unphysical if you have multiple layers, for example. Did you have any issues related to that, or you can comment on that in this context?
No, I think luckily enough, I haven't had any issues with that. Like the gradients were actually what I have seen, and the things I checked were okay, and that's why I didn't explore it too much. And
you have an idea why that might be the case?
I think because at the end, I don't have a very deep model, right? I just have to propagate stuff through some maybe like some annoying operations, but it's not very deep. So I think there's not too much space, too much room for the gradient to blow up, and also they're pretty much controlled with the learning rate, with a low learning rate. Actually, the modifications that they do to the parameters are in the good range. If, for example, if I increase the learning rate, yeah, they start going in directions that are not very good and maybe like too high. But with a low learning rate and with the way it's set up, it's working very robustly, I could say.
Yeah, it's interesting. We also have a physical model that can often help regularize the gradients.
Yeah, it did.
Yeah, very nice. Yeah, I mean, maybe the last question, you said we're still some ways away from the requirements. Have you thought about, it's a cosmology thesis, so let me ask you a cosmology question. Have you thought about the impact this would have on weak lensing science? Or how far are we away from reaching the weak lensing science goals, even if we were adapting your method?
That's a good question, but right now I don't know at which level of precision they are in for example, the shape measurement in Euclid. So maybe Andy can answer that. But so I'm not sure at which point it's going to impact or not, because at the end
we just heard PSF is the bottleneck. So
actually PSF is a very hard problem, but yeah, I'm not sure if we are 2 times over the requirements, it's going to be what's going to dominate, or if we are 5 times, it's going to be much worse, or if we are all on the requirements, we should be okay. But the question is if we are going to arrive them or not, and if we don't, at which point we are okay or not. And I think the propagation of the errors in this Euclid setting I think it's a thesis in itself. It's a very hard problem.
Good. So job security. All right. So thanks very much for your answers. Now let me go to first Martin.
Okay. Yeah. Thank you, Tobias, for this very nice talk. I think you impressed everyone with the huge amount of work that you've done over the last 3 years. And it was a great pleasure and a great honor to be part of that work. So I just want to mention that for the first part, the carbon MCCD and ground-based surveys, now your method is now a standard part of the pipeline that we've all developed here in our group, and I'm very happy about that. It performs really well. Outperforms, the state-of-the-art codes that we had before. And we're also, already reaching out to other people who might be interested to use these pipelines on other imaging data. So I think, I hope it will kind of spread around and be widely used. And also for the Euclid parts, as you know, there will be some continuation of this work in our group. And maybe Jean-Luc can comment on this some more. And yeah, this is maybe a partial answer to Andy's question. So hopefully there will be a lot of efforts to make this Euclid ready, this code. Yeah, I don't think I have a question. I think already many questions were being asked and answered. So yeah, thank you very much again.
Thanks, Martin. Jean-Luc?
Okay, so I have no question. Can you imagine? Yeah, first I would like to congratulate you for the presentation of your work. I think your talk was really great. I think you know now how to make talks, and that's also a part of the PhD. And really, you show in this talk the amount of work that you did and was very intense. And you have developed a lot of tools. And what also was very interesting is you are not only interested by developing the tools, but also by applying the tools. And Martin knows, but Benjamin also, and Jason, they know that having a software which works relatively well on simulation and having something working on real data, there is a big gap. And you took the time and you put the energy to fill the gap and to make your MCCD software working for Thesis, including the software in the pipeline and making all the validation tests, all the things. This was an intense amount of work, and it's not very clear when you show just one plot or two plots how much time you spend on that. So congratulations for all this energy and this motivation that you always show. For me, you have everything to be a good researcher. You are curious, you are motivated. You have the energy, you are not afraid of the amount of work to be done. You bring ID, very important in research. You are not afraid of real data. That's very important if you want to continue to work in the field. So you have all, to my point of view, you have all the quality to become a brilliant researcher. You are already a brilliant young researcher, but to be a brilliant senior researcher in the future. I'm really happy that you found a good postdoc, and I'm sure that you will do a good work in UK. So now I can just tell you that you will be missed a lot at Cosmostats. You were not only a good researcher in the group, but you were also a good colleague for all the PhD students. You were really like an example for them, and so thank you for the way you were for all these 3 years, even a bit more. And I'm sure that everything will be good for you in the future. And congratulations again for the work for 3 years. And it has been a real pleasure for me to work with you. Thank you.
Thank you very much, Jean-Luc.
Thank you, Jean-Luc. So that concludes the question and answer session. I don't know what the plan is right now. Do we stay here?
The best is stay here because I have a Zoom explanation. So
if I may ask the other Please come up.
Yeah.
You have to be visible.
Okay.
As the president of the jury, the soutenance, and as you can probably tell from the smiles of the committee, this was one of the easier discussions that I've had after a presentation like this, the soutenance. So we all felt that your thesis was of very high quality, that both the thesis and the significant amount of work that you've done over the last 3 years, and your presentation really demonstrated your mastery of the subject and the innovative contributions that you've made to the field. And we really appreciated your answers to our very diverse set of questions. And I think the maturity that you displayed in switching contexts and assessing the backgrounds that, and clearly also having the background to address these questions. And so as the result of our deliberations, I'm very happy to say that we would like to award you the degree of Doctor in Physics from the Paris-Saclay University. So congratulations.
Congratulations.
Bravo.
I don't know if you have any comments to make.
Yeah, I can say some words from your first time, but first of all, thank you all of the jury. I know that takes a lot of time, that you're very busy, and I gave you a very big manuscript to read. So I really appreciate the effort of reading it and reviewing it and going through all the process. So thank you very much. And I'm very happy, also honored to have such an impressive jury. So that for me is super honoring. And, okay, I guess I then continue thanking the CA for funding me. That's always something very important because they were funding all the PhD. And also, I think I have to have a big thanks to all the group where I was working at Cosmologists. First to all the students there involved. It was a very nice ambience. From the permanent people, like they're incredibly helpful, like Sam and some other people that are not here, and also to the PhD students, even the students that already finished and the students that are coming. So always like trying to transmit some knowledge. And also a big thanks to both of my supervisors. I think it was a very honor to have them from all the different points of view and like different discussions we had. They were very fruitful, and I think I would like to remark maybe two things. First, the support they gave me from the first moment. They were always super supportive, from the implementation of the method using the real data to pushing it forward to really using it, to all the part in Euclid that is hard when you still don't have results and you have to continue working until you have. So that was one thing. And then they were also super supportive on exploring different paths, and also like supervising some interns. That was like really, I think that really nice also. I learned a lot with them. Also trying to work with them was really good, and having the opportunity to supervise the students was also a great part. Besides all the questions and stuff, so thank you very much, Mark and Jean-Luc. Thank you for being my supervisors. Continuing with the thankfuls. Thanks. I would also like to thank all my friends that were here. Also people who play football, like Fred here. My interns, that there's one here, but there were already also two others. Maybe they're doing online. Well, all the people that have moved, come here to follow the the defense from Paris, from other cities in France, and even from Argentina, from my mother over there.
Congratulations.
And also the friends that came from all over the place. I'm very happy, and the people also from the CA following. So big thanks to them, and also from the people that may be still following on YouTube. Instead of seeing or using YouTube. Thank you all. Well, I'm going to speak in Spanish a little bit. Bueno, gracias a la familia que está siguiendo ahí por YouTube. Un abrazo grande. Que bueno, fue todo en inglés. Espero que hayan entendido algo. Y a todos los amigos que también seguro están siguiendo por ahí. Así que muchas gracias a todos por seguir y por el apoyo siempre. Y nada, muy contento en este momento. So, thank you all, and that's I think that's.
Bravo.
Thank you very much.
So,
Bye.
congratulations.
Bye. Thank you very
Bye,
much.
congratulations.
Félicitations, Tobias.
Voilà.
Thank you.
Bye.
Et au revoir.
Bye.
Bye bye.